Let's start chapter 5. Today we're going to start with 5.1, area between curves. So far we've learned to calculate area under a curve. So if you're given a function f, let's assume f is above the x-axis. So let's say you have f and you want to calculate this area under the function f from a to b. So this area would be, by definition, be the integral from a to b of f of x dx. If it was below the x-axis, then this integral would be negative. So the area, you take an absolute value or you multiply a negative sign to it. Today, what we're going to talk about is the area between two functions. So which means, assume you have the function f and there is a function g. Call this g. And then our problem is, what is this area between the two functions? And it's quite simple to figure out. We know the area under the function f. We can figure out the area under the function g, which would be that. So this red area would be basically from a to b of g of x dx. Then the area in between would be the difference between the two areas. This is area under f, area under g. So the area between the two functions f and g would be subtracting the two integrals from each other, which is going to give us the difference between the functions. Since they have the same boundaries, you can write it as one integral. So it would be difference between f and g dx. The only thing that you have to notice is we assume that the function f is always above the function g. That way, this part f minus g is always positive. Therefore, the integral is going to give you a positive area. You're not going to get negative value. So we assume that if f is always greater than or equal to g, and for some continuous function over the interval a to b, then the area between the two functions would be the integral from a to b of f of x minus g of x dx. Again, in this assumption, we assume that f is always above g. We'll talk about what if f is not always above g. What if there is a intersection between the two functions later. So for example, let's say if we had this is g and f was this one, and you wanted to calculate the area between the two functions, which means you wanted to find out this area from a to b, what you need to calculate is the top function g minus the function below, because you have to figure out this area and the bigger area, subtract those two from each other. So the top function is g, the lower function is f, and you integrate from a to b. This will give you the area between. So depending on which function is on top, you always subtract the top from the bottom. Okay. So here's an example. Let's find the area between the two curves y equal to x squared plus 1 and y equal to x, and bounded by these two endpoints. X equal to 0, x equal to 1 is basically over interval 0 and 1. This is what it means. So let's figure out what is the graph of these two first look like. And I'm going to only focus on the interval 0 to 1, so I don't really need to graph the function overall. From 0 to 1, x squared plus 1. X squared is the parabola, plus 1 is shifted up 1 unit. So it will look like this. At 1, you would have y value of 2. Say 2. And at 0 has y value of 1. This is the function y equal to x squared plus 1. And the other function, if y equal to x, would be a straight line 45-degree angle line. Something like this. This is y equal to x. And again, I only focused on from 0 to 1. What we want is this area between. From 0 to 1. From x changes from 0 to 1. Let me erase the y values. So how do we find that? The top function is x squared plus 1. The lower function is x. And we want to find the area between. So a would be from 0 to 1, from a to b. of the top function, x squared plus 1 minus the function below, x dx. It's good to use parentheses and brackets just to make sure the subtraction, if the function, the lower function is not that simple, you have to distribute this negative sign into other terms. So it's better to use parentheses. Okay, so what we get is from 0 to 1, x squared minus x plus 1 dx. I put them in order just to take the antiderivative. Find the antiderivative and evaluate. X squared antiderivative would be x cubed over 3 minus x squared over 2 plus x. You don't need constant c since you have boundaries, so from 0 to 1. And replace 1, replace 0. If you replace 1, what you get is 1/3 minus 1/2 plus 1. If we replace 0, we get 0 minus plus 0, so minus 0. And what we get is 1/3 minus 1/2 plus 1. That's 1/2 plus 1/3, which is 5/6. So the area between the two functions turned out to be 5/6. Super easy to calculate. The only thing is that you have to find out which one is the top function, which one is the lower function. Graphing kind of helps. Sometimes if you rearrange this, instead of calculating that way, if you would have calculated from 0 to 1, x minus x squared plus 1, you would have done it the other way. Instead of the top function minus bottom, if you would have said bottom function minus the top function, what you get at the end by calculating is exactly the same value, but opposite. You'll get negative 5/6. So this tells you that basically you subtracted the functions in the wrong order. Okay. Here, one more example. Find the area of the region enclosed by these two curves. So this is kind of typical to be asked about these as well. Let me show you. Sometimes you're not given the interval. So you're given something like two curves. One of them is f, the other one is g. And they ask you to figure out this closed area. This area enclosed between the two functions. What you need to figure out is first these two intersection points, because you need to find out the boundaries. What is the A, what is the B, the endpoints. And how do you do that? At the intersection points, the y values are equal, the x values are equal. So what it means is at those intersection points, f and g must be equal to each other. Both the x coordinate and y coordinates are equal. So if they ask to find the area in an enclosed region, what you need to do is, by the way, the area would be simply from a to b of g minus f, the top function minus the lower function, over this closeness. First, you need to figure out what are the two endpoints. That means first solve this equation. When does f equal to g? So here, this example, let's figure out where is the intersection of these two curves. So figure out where 2 square root of x minus 1 equals to x minus 1. Yeah, this is you can square both sides just to solve this equation. So you get 4 times x minus 1 equals x minus 1 squared. I squared both sides. Raise both sides to power 2. What you get is, let's move stuff around and say 4x minus 1 minus, okay, let's do it the other way. The other way is easier. X minus 1 squared minus 4x minus 1 equals 0. They both have x minus 1 in common. X minus 1 factored out, you have x minus 1 left minus 4 equals 0. So what you get is x minus 1, x minus 5 equals 0. So there are two solutions, x equal to 1 and x equal to 5. You could have guessed those two solutions. Where do these two equal to each other? If you replace 1, you get 0 for both. If you replace 5, you'll get 4 for both y values. So what does it tell you? It tells you that if you draw these two curves, however they look like, I can draw it maybe precisely. This is how 2 square root of x minus 1 looks like. and the other one is y equal to x minus 1. That's a curve, a straight line shifted up 1 unit. Something like, let me fix this. How do we, x minus 1 at 5, and here, sorry, there is this square root is shifted to the right a bit, at the 1, starts at 1. That's how 2 square root of x looks like, and the other one is a straight line starting from 1. Kind of looks like this. This is y equal to x minus. And you notice this enclosed area. The endpoints are supposed to be at 5 and at 1. These are the two intersections. This is the only closed region between these two. So how do you find the area? The area would be integral from 1 to 5. Here comes the endpoints that we found. Now, the top function minus the function below. What is the top function? The top function is square root 2 square root of x minus 1 minus the function below, x minus 1 dx. You fix this. Okay. You notice that this is not that easy to calculate. Let me first rewrite this a bit more clearly. From 1 to 5, 2 square root of x minus 1 minus, okay, instead of that, I'm going to write this power 1/2 minus x minus 1 dx. Okay, we can calculate the antiderivative of that, but the problem is we cannot calculate the antiderivative. This one's simpler. So what we need to do is we use substitution. We learn substitution method. I'll pick a u to be x minus 1. Composition of two functions. One is square root of x, the other one is x minus 1. So I pick the inside function to be u. The derivative of u with respect to x would be 1. Derivative of x minus 1 is 1. So du equals dx. Multiply both sides by du. And we can change the boundaries as well. If x is 1, what do we get for u? U would be 1 minus 1, which is 0. If x is 5, what do we get for u? U would be 5 minus 1 equals to 4. I use this to figure out what is u. So I can rewrite this integral and say, okay, this area equals to integral from 0 to 4 to u to the power 1/2 minus x minus 1 is again u, and dx is, we figure out dx equals du, so du. Right, dx equals du, and instead of x minus 1, we replace du. Let's simply calculate this. The antiderivative of 2u to the power 1/2 would be 2 times u to the power 3/2 divided by 2/3. Sorry, divide by 3/2 minus u to the power 2 divided by 2. Evaluate it from 0 to 4. So you can simplify it a bit more. It would be 4/3 u to the power 3/2 minus 1/2 u squared, evaluated from 0 to 4. If you replace 4, what you get is 2 to the power 3, which is 8 times 4, 32 divided by 3, minus the other one would be 8. And if you replace 0, you'll get 0. So this is if you replace 4 and replace 0, and simplify that is 32 times 3 is 24, 24, 32, it would be 8/3. So we figure out the area between the two curves, and it's simply 8/3. Okay, just be careful with the calculation. The calculation is kind of important. You don't mess it up. Okay, so if you have an enclosed region, you first have to figure out what are the endpoints. Where is the interval that you want to evaluate the integral over? Okay, So in these examples that we did, there was always a function above the other function. There was never crossing over and figuring out, okay, what if the function doesn't always stay on top and the other function goes over? So here, what if we deal with that case? What if you have a function g and f act as if g is below in some area, like in this section, g is below f, and in the other part here, g is above f, and we want to calculate the area between the two functions. We want to figure out what is this area, what is this area, and figure out this area, and add up all those three. So what you need to do is figure out these intersection points. Here is C, here is D. Figure out the integral in each section. In this part is g above f function, so we write integral from a to c of g minus f. Then we add it to the integral in the next section. In this portion, in the yellow section, is from c to d of f is above g, f minus g, plus in the last section would be from d to b of g minus f, because g function at this point is above the f function. This way the integrals are always positive, so you get areas. If your integral gets negative, turns out to be negative, that means you've calculated the area in the wrong order. So what you can do is basically calculate each one of these. If they turn out to be negative, that means you've calculated in the wrong order. So what you need to do is just take an absolute value at the end. Or you can look at the definition of this integral. It says, okay, take an absolute value of the difference of the function. That means you have to break it up and figure out in which section the function is above. It's basically breaking down the integral in this way. If you have more than two intersections, you have to break up integral more and more. Okay, you can always do this, or you can calculate always f minus g in each section from A to C, from C to D, and from D to B of f minus g. F minus g. What do you get at the end for this? Would be negative. This one would be positive. This one would be negative based on this graph that we have. So what we avoid is we take an absolute value always at the end to make it area to be positive. And then you add up these three. That's another option. I recommend make sure that first you get a positive value. That means the order of subtraction is correct. But if it turns out to be negative, you don't need to worry. Just interchange the f and g and you calculate. You get exactly the same numbers, but the opposite side. So here, let's try this one. Find the area of the region bounded by the curves y equal to sine x, cosine x over the interval 0 to pi half. So let's draw the curves to notice how the function behave. Actually, not always you can draw the function. So let's assume that we don't know. And you want to solve this. Here, let's say pi half is here. You only want to focus from 0 to pi half, because that's the area that we want to evaluate the integral over. So what we want to do, find out if there is an intersection between these two functions. So let them equal to each other. Sine x equal cosine x. And if you go through the unit circle, when do you get sine x equal to cosine x is the same as divide both sides by cosine, is the same as saying where tangent x equals to 1. And this happens when x equals pi over 4. And 5 pi over 4, 3 pi over 4, and so on. But the only one that is between the interval 0 to pi half is pi over 4. So this is the only time that two functions are equal to each other. And the curves, one is cosine, one is sine. This is how sine looks like. And cosine starts from 1 and reaches pi half. So this is cosine x, the other one is sine x. Okay, maybe I should have used a different color. Here, let me change this to blue. sine x. Okay. So now, what you notice is now I have to break up the integral. If I want to find the area, I'll calculate the area as if I'm going to calculate two integrals, 0 to pi over 4 plus from pi over 4 to pi half from the intersection point, from 0 to the intersection point, from the intersection point, if there is one more intersection, to the next one, to the next one, and so on until I end the end point of the interval. And you can always do top function minus bottom function. I want to show you that it doesn't really matter if you change the order. So I'll always do cosine x minus sine x. Cosine x minus sine x. I'll evaluate each one. Dx. Dx. I'm going to keep this format. Let me actually shift it up a bit. Okay, let me move this the other side. Kind of pi over 4 here. And let's move this up. Okay. So we want to find those two integrals. I'm going to calculate the integral from 0 to pi over 4 of cosine x minus sine x. By the way, the correct order is cosine x minus sine x from 0 to pi over 4. Cosine is on top minus the sine function. This is correct. From pi fourth to pi over 4, it's supposed to be sine x minus cosine x. You should say, okay, this instead of cosine x minus sine x, you should write sine x minus cosine x. But if you do it this way, you'll notice that it's going to be exactly the same number, but the opposite. Whatever you get, if you do sine x minus cosine x, let's say you'll get pi over 3 or whatever. Then if you do it in this order, you'll get negative pi over 3. I'm going to avoid having negative by doing it as sine x minus cosine x. And it's kind of important, either you use absolute value at the end or you use the right order. So homeworks, normally they ask you to write the top function minus the bottom function. So rearrange this in an order that always the result of the integral is positive. If you do cosine minus sine x from 0 to pi over 4, what you get is the integral of cosine is sine. The integral of sine is negative cosine. So you'll get sine plus cosine x here. Evaluate from 0 to pi over 4. If you replace pi over 4, you get root 2 over 2, root 2 over 2. If you replace 0, you'll get minus 0 minus 1, which is going to be root 2 minus 1. So this integral is square root of 2 minus 1. And if you calculate the other integral from pi over 4 to pi half of sine x minus cosine x dx, you get negative cosine x minus sine x evaluated from pi fourth to pi half. What you get is, if you replace pi half, cosine would be 0, so you get minus 0, negative 1, plus, if you replace pi half, we get negative 1. If you replace pi fourth, you get minus negative root 2 over 2 minus root 2 over 2, which is going to give you root 2 minus 1. Okay, so this one will give you exactly the same term, root 2 over minus 1. The important thing is if you would have done it in the other order. So by the way, if you add these two, what you get is 2 square root of 2 minus 2. This is our answer. Add this number plus the other number. The important thing is in the second integral, if you would have done it the other way, instead of sine minus cosine, if you would have done cosine x minus sine x dx from pi fourth to pi half, what you get is not root 2 minus 1, but negative root 2 minus 1. You'll get this number. which is exactly the same, just negative. That means it tells you that you did it in the wrong order. Okay, so the integral will kind of tell you if you've messed it up, the order of the function. Okay, so we found the area between these two, so which means we found this section plus this section. Added up those two. Here, one more example. What if you have three functions and they want the region enclosed by? Again, sometimes you can get certain shapes. Something like, let's say you have this function, there's another function, and there's a third one, process like this, and you want to figure out this area. So what you need to notice is figure out where are these important points, the intersection of these points, and graph the function so you can break it up into multiple pieces. So first always is to figure out what are the intersection of each curve with the other. I'm going to focus on 1 over x squared and x, these two, intersection of these two functions. You can call them graph 1, function 2, function 3. You can give them name f, g, and h. Okay, so where does this happen? You can multiply both sides by x squared. You'll get x cubed equals 1, and take a cube root, so x would be simply 1. So this is the intersection of the curve 1 and 2. They intersect at x equal to 1. How about if you focus on curve 1 and 3? Where do they intersect? Is if you have 1 over x squared equal to 1 over 8x, you can again multiply both sides by x squared and multiply by 8. You'll get 8 equals x cubed. If you take a cube root, x would be 2. So you figure out this intersection as well, the intersection between curve 1 and 3. And how about the curve 2 and 3? Where is the intersection of curve 2 and 3? What you get is, x equals 1 over 8x. When does this happen? It happens when x equals to 0. You can multiply both sides by 8 and subtract. That happens at x equal to 0. These are the intersection of all three curves. Okay, this helps when you graph the function. So let me graph the functions precisely. So you would make more sense of how to calculate the area enclosed by these. Because these points of intersection is kind of the important ones. 1/8 of x is a straight line with a slope 1/8. So this is curve number 3. Curve number 3. And I graph it up to 2. And let me change colors. Curve number 2, y equal to x. They intersect at 0. The line 2 and 3, they only intersect at 0. This is, say, curve number 2. And curve number 3, they intersect 1 and 1 over x squared, and x will intersect, so 1 and 2 intersect at 1. So let's say 1 is here. 1 over x squared has a vertical asymptote at 1/2. So it's kind of looks like this. And the intersection with the curve 3 happens to be at 2. This is 2. Shift this a bit to the other side. Happens to be at 2. So you notice that these points, we found that already they're x values. And it should match up with whatever you found. At 0, 2 and 3 will intersect. At 1, the curve 1 and 2 will intersect. And at 2, the curve 1 and 3 will intersect. So what we need is to find out what is this area. How do we find it? Here's the important part. You have to break this up into 2 pieces. Up to 1, this closed region. Up to 1, it uses 2 functions. What are those functions? The blue function and the green one. So it uses the function x and 1/8x. After 1, what happens is you have the other two functions. One of them is 1 over x squared. The other one is 1/8 x. So if I want to calculate the integral, the area, I have to break up the area and say the area in the enclosed area is from 0 to 1. It's the top function minus the bottom function, which is x minus 1/8 x, and dx, plus from 1 to 2 is the area of the top function, 1 over x squared, minus 1 over 8 x. And then I will calculate these integrals, add the result up, and that would be the area between these curves. And so the enclosed area would be calculated this way. Okay, so let's do that. Let's figure out each integral separately. Let me change this color back. Okay, so first I want to find out what is from 0 to 1 x minus 1/8 x dx. I can simplify this function inside, by the way. From 0 to 1, x minus 1/8 x is 7 over 8 x dx. Now it's simply, the integral would be 7 over 8 times the integral of x is x squared over 2, evaluated from 0 to 1. If you replace 1, we'll get 1/2 times 7 over 8 would be 7 over 16. And if you replace 0, minus 0. It's simply 7 over 16. Okay, so this first integral. To figure out this area is 7 over 16, corresponding to this yellow area, 7 over 16. And then the other part of the integral, from 1 to 2, 1 over x squared minus 1/8 x dx. You can always write this integral, this 1 over x squared as x to the power negative 2 minus 1/8 x dx. And what you get is the integral of x to the negative 2 is x to the negative 1 divided by negative 1 plus, minus 1 over 8 x to the second divided by 2, evaluated from 0 to 1. From 1 to 2. And you can rearrange this again. 1 over x, negative 1 over x, minus 1 over 16 x squared, evaluated from 1 to 2. Be careful with these calculations again. It's always messy to deal with these numbers. So if I replace 2, what you get is negative 1 over 2 minus 2 squared is 4. 4 times negative 1 over 16 is 1 over 4. This is if we replace 2. If we replace 1, you get minus 1 over 16. So this numbers will add up to negative 1/2 minus 1/4 is, this is negative 3 over 4, minus negative 1 minus 16 is minus 17 over 16. With the negative becomes plus 17 over 16. And if you do common denominator multiply of 4, you get negative 12 over 16 plus 17 over 16 is basically 5 over 16. And you notice it's important that the result is positive. That tells you that you correctly subtracted the top minus the bottom function. So what we found is 5 over 16 in this area. And now what is the total area? 7 over 16 plus 5 over 16. That is 12 over 60. Is 3/4. All that work, and we found out that, okay, this triangle, this shaded triangle, has area of 3 over 4. It's not an approximated area, it's an exact value. Okay, there was no approximation. We used integrals, and specifically we figure out the area. So if you're dealing with enclosed areas, make sure that you figure out the intersection point precisely. And use the correct function, the top function, the minus the bottom function. Now, it's important that you notice curve 1 has no effect in the area from 0 to 1, because the enclosed region is between x and 1/8 over x. And in the other part, the curve 2 has no effect, because if you're figuring out this area here, what is the top function is 1 over x squared, the bottom function is 1 over 8x. So you subtract those two, you ignore the function x. Okay, this is 5.1. I'm going to stop here. Next time we're going to talk about the volume created by curves, and we use integrals to calculate volumes, certain volumes. I'll stop at this point.